Section 3.2 is pretty short, and it really just has to do with the graph of a derivative and how it relates to the graph of the original function, and then also the link between differentiability, which is being able to take the derivative of a function, and continuity of a function, which we talked about at the end of the last chapter. And there is a link between whether or not a function is continuous and whether or not we're able to take its derivative. Because we can't take the derivative of every single function. Remember, the definition we learned in 3.1 for a derivative so far contains a limit. And we learned in the last chapter that there are some limits that don't exist. So if there's some limits that don't exist, that means there may be some derivatives that don't exist. So we're going to start by talking about the graphs of derivatives. And we're not going to get too technical here. And I'm going to show you something on Desmos that can help you out. Desmos, I've used it a couple times before. It's just an online graphing calculator. It's a little bit more user-friendly than your TI-84. It's got some extra functions on it that might come in handy. So what we've talked about so far is that derivative equals tangent slope. And for the graph of a function, the tangent slope can be different at all the different points. So your derivative very often is some function of x, which means as you plug different x values into your derivative, it's going to change. So it takes on all sorts of different values in different places. So the derivative itself is a function and can have its own graph and create its own curve. So the easiest way to do this, to figure out the graph for a derivative, is to look at the original graph. So let's say we're just going to look at the graph. I'm not even going to give the equation for this because we don't want to have to go through the whole difference quotient limit process stuff. We just want to look at the graph. So let's say this is f of x. I'm going to try to do this on the same graph. Hopefully it doesn't get too nasty. Remember, the derivative tells us tangent slope. So one of the first things you should try to point out when you're trying to find the graph for a derivative is where the tangent slope is 0. So you need to remember from algebra class what a slope of 0 looks like. And a line with a slope of 0 is a horizontal line. So we would have a slope of 0 anywhere we have the top of a hill or the bottom of a valley, anywhere we have relative maximums or minimums. So at this point right here, approximately, and this point right here, we have a tangent slope of 0. So if you were to graph a little imaginary tangent line there, it should be perfectly horizontal, which means derivative equals 0. Derivative equals 0. Now, if you look at the tangent slopes around those points, so before this first point, if you draw some tangent slopes, all those tangent slopes are pointing up. They're all positive. So here, f prime of x is greater than 0. If you look at the tangent slopes in this section, they're all pointing down. So in this section, f prime of x is negative. And then once we get past our next one and move over to this section, all of our tangent slopes are back pointing up again. So f prime of x is positive. And we can use that information to come up with just a rough sketch of what we think our derivative function is going to look like. And I'm going to do this one in blue. So we're using these derivative values as actual points on the graph. So when we had f prime equals 0, well, for a normal function, when it equals 0, that's an x-intercept. So my blue graph now is going to be my derivative function. So equals 0 means x-intercept. And then we had another one over here. Equals 0 means x-intercept. So all the way on the left-hand side, we had positive derivative values. So anywhere we have positive values, typically the graph is above the x-axis. And then in between our two zeros, we had negative derivative values, which means our graph is below the x-axis. Negative values. And then after, over on the right, after that second zero, we're back to positive derivative values. So our derivative function goes back above the x-axis into the positive territory. So this blue graph could be our f prime of x. Wherever we had a horizontal tangent line, that coincides to an x-intercept on our derivative function. Horizontal tangent line coincides with an x-intercept on the derivative function. Positive slopes, if you draw tangent lines, positive slopes means we have a piece above the x-axis. Negative slopes means piece below the x-axis. Positive slopes means piece above the x-axis. So this is an example for a polynomial, and we don't even know the equations for these lines, or these functions. But they're definitely polynomials. And we can do them for other types of functions as well. So what we did here is first we found where the tangent slope was equal to 0, and then we analyzed what was happening in between those zeros. So we looked to see whether the tangent slopes were positive or negative in between the zeros. So we check for positive or negative tangent slopes between the zeros. Another quick example. And this one's a little bit different, because this one is not going to be a polynomial. If we have, let's say, it pretty much looks like 3 linear functions all pieced together. This is our f of x. And we want to try to estimate, get an idea of what our derivative function looks like. So there's technically nowhere where we have a horizontal tangent line. Now, we do kind of have the bottom of a valley and the top of a hill, but we did an example back in the last chapter where we tried to do a limit here on a limit on a absolute value function, and it turned out that the limit for the slopes did not exist, because as you approach in from one side, the slope is negative. As you approach in from the other side, the slope is positive. And there's no gradual change from one value over to the other. One value just stops and completely jumps to the other. So we have to, with those two values, have to meet in the middle somewhere in order for that limit to exist. So we're going to talk about this in a few minutes, but technically derivatives do not exist at sharp corners. This is the first place that we see here and that we're going to talk about where we cannot take the derivative. And another word for sharp corners, our math word for it, is a cusp. This is a cusp. This is a cusp. And the derivative at those two spots do not exist. Which means our f prime of x graph is not going to exist at those two spots. We are not going to have a functional value for f prime there. But I do know before this spot, my tangent slopes are all negative and they're all exactly the same. I don't know exactly what it is, but it looks like it's about -1. So if I say this is -1, all of the tangent slopes are -1 until I get to that sharp corner. But I don't actually have a derivative at that sharp corner, so I've got an open circle there. Now, after the sharp corner, my slopes jump to, it looks like maybe +1. And they stay consistent because it's a straight line. So if this is +1, my slopes jump to +1. And they're going to do that and stay there until they get to my other sharp corner. All the slopes are exactly the same for that middle section. When I get to my other sharp corner, all of a sudden slopes change again, and they go back negative again, tangent slopes. This time, they're a little bit steeper negative. So they're not -1, maybe they're -2 now. So I'm going to extend my graph down a little bit further so I can do -2 here. So we'll say that's -1 and that one's -2. So now this last piece, it looks like we have an even steeper negative slope. So we've got a -1 slope for this back section. There is no slope here at this point because we've got a sharp corner. And then we've got a positive slope. The only indicator that it's positive is the fact that this blue line is above the x-axis. That is what's telling me that the slope is positive. These other two pieces are below the x-axis, which means they have negative values. The slopes are negative. This one is lower, which means it's a steeper negative. So we get to our second point, our second cusp, and derivative does not exist there. That's why they're both open circles, and it gets negative again and even steeper. So that is back down in the negative territory, but it's even lower because it has an even larger negative slope. So my blue graph is our attempt at the f prime graph. So we're just kind of trying to make a guess here at what is happening with our tangent slopes and putting it all together to make a new graph. Now, if you actually know what the equations are for these functions, you can use Desmos to graph them. Desmos has a derivative grapher in it, which can be really helpful. So let's say that we know we've got the function x cubed minus 2x squared plus 5x. I don't like that. And I'm going to zoom this sum to make it prettier and bigger. And then I'm going to add another function in here. And I'm going to, for number 2, I'm going to say graph the derivative of that. So I'm going to go to functions, and I'm going to go to miscellaneous. And you will see under miscellaneous, we have d dx. So in the section 3.1 video, I had said that d dx is one of the notations that we use that means take the derivative of. So they're directions that mean take the derivative of. So in number 2, in equation number 2, I want to take the derivative of x cubed minus 2x squared plus 5. So d dx, and then I'm going to do my same function again. X cubed minus 2x squared plus 5. So the blue graph is the derivative graph, the red graph is the original. And let's look here and see what's happening. So what we just said when we did these by hand is that we would look for places where the original function had a horizontal tangent line, and it looks like our original function has a horizontal tangent line right here, which means our derivative function should have a 0 right there. So if we follow that down, it's absolutely true that our derivative function is crossing the x-axis right there. And then it also looks like our original function has a horizontal tangent line here. If you follow that down, it is absolutely true. Our derivative function is crossing the x-axis. And then if you look and see what's happening in between those zeros, slopes are positive in the left section. So this blue graph is above the x-axis. Slopes are negative in the middle section. If you draw some tangent slopes, they're going to point down. So this middle section here is all below the x-axis. And then once we get past that, that last 0, we're back to positive tangent slopes again. You can draw any little tangent line there and they'll all be pointing up. So this last blue section here goes back above the x-axis, which means positive values. So you can use Desmos to help you do these really quickly. You might have to zoom in and zoom out a little bit. If you're, I'm on a tablet, so a touchscreen tablet, so I can just zoom in and out with my fingers. You can always zoom in and zoom out with these buttons over here on the side, the plus and the minus, to help you out. If you have a scroll wheel on your mouse, that can zoom in and zoom out as well. And if you click on the wrench, I believe that you can define what you want your window to be, just like we define the window on our calculator. So you can put X is between an upper and lower bound, and Y is between an upper and a lower bound if you want. If you know a specific range you want to look in. So Desmos can be really, really useful and really helpful, and it's got even personally, it's got, for me, I think it's more useful than the graphing calculator. And you can even use your mouse to click on these points if you want to know exactly what some of these points are. So I can see that place where we have a horizontal tangent line is 0, 5. So it's at an x value of 0, and go down here and it's crossing the x-axis at 0. And then I can see it's got a horizontal tangent line at 1.333, which is 1 1/3. And I can go down here and see it's crossing, the derivative's crossing the x-axis at 1 1/3. And we can get those points just by using our mouse and touching the graph, where on our calculator, we would have to go to the calc list and choose a function and do left-bound, right-bound guess. It takes a lot longer to do it on the calculator. Desmos is a lot quicker and more user-friendly. So I really like Desmos a lot. So what we saw here with this graph is that derivatives do not exist at sharp corners. And there are some other places that derivatives do not exist, and we're going to start a little list here. So undefined and do not exist, they mean the same thing. So some places where we cannot take the derivative. Well, the derivative is defined using a limit we just saw in the last section. So anywhere we can't take a limit, or anywhere the limit does not exist, is going to be a place where we can't do the derivative. So we just saw when we have a sharp corner, which means our left slope and our right slope are not coming together to equal up to the same number, our derivative is not going to exist. And that is when we have a very sharp corner. So that's on something like an absolute value function graph. Those are the ones that usually have sharp corners. So derivatives are undefined at sharp corners. And this is like on absolute value graph at 0, 0. Now we can do the derivative at other points on the absolute value graph. We just can't do it at the sharp corner. We just can't do it right there. We can do it at the other places. We just can't do it at the sharp corner. Some other places that we cannot do derivatives. When f of x is not continuous. If the graph is not continuous, we can't take the derivative. If it's not continuous, there are several different ways that would make it not continuous that we talked about in the last chapter. One of them is if the limit does not exist. Another one is if the functional value does not exist. And then the third one is if the limit and the functional value are not equal to one another. So all of that was in the very last section of chapter 2. So if any of those three criteria hold, that means our function is not continuous, and that means that our derivative is going to be undefined. The shortcut way to decide if your function is continuous, if you actually have a picture of the graph, is to see if you can draw the whole thing from start to finish without ever lifting your pencil. If you can draw the entire graph from start to finish without ever lifting your pencil, then it's continuous. So the three criteria we said that would make it not continuous is the limit is undefined, or the functional value is undefined, or at one particular spot our limit does not equal our functional value. And we had some little names for these. If our limit is undefined, that means we had a hole in the graph. If our functional value, nope, I'm sorry, I've got this backwards. Let me go back. If our limit is undefined, that means there's a gap in the graph, because that means our left-hand side and our right-hand side are not matching up. So there is a gap. If the functional value is undefined, that means there's a hole. There's just a point missing. And then if the limit and the function are not equal, the limit exists and the function value exists, but they're not the same, that means that there's a jump. That means we're drawing our graph nice and smooth, but then for one instant, we jump away to mark a point and then we jump back onto the graph. So gaps, holes, and jumps. Those were our 3 things that we had to avoid in order to be continuous. If our function's not continuous somewhere, we can't do the derivative there. The third spot where we do not have a derivative, where we can't take a derivative, is if our function has a vertical tangent line. And an example of a function that has a vertical tangent line is the cubed root function. If you look at the cubed root function, it looks very similar to the x cubed function, except it's laying on its side. And I will get this right eventually. Yep, that's a good one. This is the graph of the cubed root of x. Most of your tangent lines are going to not be a problem at all, but there is one spot on this graph where we have a vertical tangent line, and that is here at 0, 0. If you draw a tangent line there, it will be perfectly up and down. And remember, derivative is slope of a tangent line. And if the tangent line is vertical, what is the slope of a vertical line? It's undefined. The slope of a vertical line is undefined. So anytime we have a vertical tangent line, we have an undefined slope. We have an undefined derivative. Because slope is derivative, and a vertical tangent slope would mean a undefined derivative. Undefined tangent line, undefined slope. All of them mean the same thing. Okay, so this is an example of a function, and 0, 0 is the only spot that messes us up. We can do derivatives everywhere else. It's just at 0, 0 that we would say the derivative is undefined. If we know that our function is differentiable, if I know I can take the derivative and my function has derivatives and tangent slopes everywhere, then that automatically guarantees that my function is continuous. This is a way that we can prove a function is continuous. If we can find the derivative and find a value for a tangent slope on the graph everywhere, then that automatically means that it's going to be continuous. So if f of x is differentiable, then it is continuous. And differentiable means that we are able to find the derivative. And then the contrapositive of this is also true. If f of x, and we just wrote this as criteria number 2, I believe, if f of x is not continuous, then f of x is not differentiable. So what I just did there is I switched the criteria and put not in front. If we know the function's not continuous at a certain point, then we will not be able to take its derivative there. Or if I know I'm able to take the derivative, that means the function must have been continuous. So there is a relationship between being differentiable and being continuous. So that's really all there is in this section, is kind of playing around with the graph of a function and trying to use it to see if you can come up with the graph of a derivative. So just keep in mind that derivative means tangent slope. And a good strategy to use, especially when the graph has got a lot of stuff going on, a way to organize this work is to first find where your tangent slope is equal to 0. That's where we have those horizontal tangent lines. That's where your derivative is going to have x-intercepts. And then once you know where it's going to have x-intercepts, we need to decide whether it's going to be above or below on either side of the x-intercepts. So look and see if your tangent slopes are positive or negative on either side, and that will tell you whether you should draw your derivative going up or going down from your x-intercepts. And then you can also use Desmos to help you. But make sure you understand what's going on, because you won't be able to use Desmos on your test. So on your homework, don't work the problem just until you get it right. Work the problem until you understand it, because your test this time is going to be on paper and it's going to be proctored. Our goal is not just to get 100 on our homework. Our goal is to understand the homework problems. Make sure that we understand them.